Hello, in this video we're going to be talking about traveling waves. Some of the most basic foundational information about waves that you need in the IB and to understand how waves work. All right, here we go. All right, so when we call these traveling waves, and what is traveling, you might ask? Well, what's traveling is really energy. Energy is the key thing that's moving in a wave. That is maybe the most important thing to know about a wave, is that what is moving is energy. We say the wave propagates energy through space. It carries it from one place to another. That is the job of a wave. Right? So there will almost always be some material through which a wave moves. A water wave, of course, travels through the water. A sound wave travels through the air, so on, so on. The thing is, and this is one of the first things that might be a little counterintuitive, but you have to think about it and picture it. The energy is moving, but the particles are not. I mean, they're moving up and down, but they're not really displacing. They're not moving from point A to point B. They're not traveling in the same way that the energy is. So here's a classic wave here, and we're looking at all the particles of a medium. So maybe this is a simple wave on the water. There's a rubber ducky over here bouncing up and down, creating ripples on the surface of water. And here's all the little water molecules bouncing up and down, it looks like, as the wave moves by. All right, or it's people in a stadium throwing their hands up and down and making the wave going around a stadium, right? But in either case, the people don't like run down the rows of the stadium. And in fact, the water doesn't move side to side. Watch this. You can, focus on the wave itself, I guess, first, the hump as it moves. And like you can see some left to right motion, I think, if you unfocus your eyes a little bit. But watch any individual dot, it only moves up and down. All right, so the idea is that the wave only transfers energy, it does not transfer matter. Right, the ocean is constantly delivering energy to the beach to erode rocks and turn them into sand. But the water from the ocean is not displacing onto the beach, or else the beaches would be flooded. The ocean is still in the ocean. So yes, they can come in and crash, but they go back. But the energy is constantly moving from point A to point B. All right, so energy is transferred by a wave. That's perhaps the most key idea behind this subtopic and maybe even waves in general. They transfer energy. All right, and instead of looking at a wave, we can also look at a wave pulse. In class, we may have made these with some slinkies. You can make a single pulse too, and the same idea. This is a pulse that carries energy from one place to another, rather than, say, a continuous wave. Okay. So let's define a few. That type we were looking at is called a transverse wave, where the key is how the particles are moving compared to how what we typically call the wave is moving, or the direction of the propagation of energy. So the energy, let's say in that last picture, was moving side to side, and the particles are moving up and down. So they're vibrating perpendicular to the direction of travel. This is a common type of wave. This is probably the most classic type of wave you first think of. A wave on a string, or a wave if you're typically making it with a slinky, shaking the slinky side to side. It turns out electromagnetic waves, which we'll get into a little bit later, are transverse waves as well. The stadium wave is another good example, right? The people stand up and sit down, and the wave moves side to side past them. So those are all transverse waves. All right, when looking at a transverse wave, there's a couple things we can define. The first thing is wavelength. Wavelength in physics, as well as period, are very specific things, especially if you have some math experience with this. It's easy to get a little sloppy, so be careful. A wavelength is a distance. It's measured in, meters usually, or centimeters, or whatever you want. A wavelength is a distance, and it's the easiest way to think of it is it's the distance between, say, crest to crest or trough to trough. So we'll call the tops of these waves the crests, the bottoms the troughs. So this distance represents one wavelength. That's assuming we're looking at a picture of the wave here. In other words, there's no time in this picture. All right, so wavelength is the literal physical distance peak to peak. All right, there's a little bit more of a mathematical definition here, 2 points in phase, but the easy way to do that is peak to peak. All right, frequency for a wave, you know frequency a little bit from oscillations. And for a wave, it's the same kind of idea. We measured in hertz, and it's really equal to the number of vibrations per second performed by the source of the wave. Something is making that wave. That's the thing that's like oscillating and moving. So again, if there's a rubber ducky floating up and down on the pond, and the rubber ducky is moving up and down 10 times a second, then it's got a frequency of 10 hertz, and the wave will also have a frequency of 10 hertz. You can also think of it as the number of crests that pass a fixed point per second. So if that rubber ducky is bouncing up and down 10 times per second, and you just watch this one point in space, it sure turns out that you might expect to see about 10 crests move by you every second. Right? Still measured in hertz, which is an inverse second. And amplitude is the maximum displacement of a wave from its rest position. So the particles, their maximum displacement. So again, same sort of definition as in harmonic motion. When we talk about amplitude, we're really talking about the particles that make up the wave are at most, this high. Different than displacement, just like in harmonic motion. It's the maximum displacement, so I guess it's a specific displacement. All right. Now let's look at the exciting equation, the wave equation. It's a big one, and it's a very simple one. All right, so we're going to use a variable for wave speed. The IB are insane, and they use lowercase c for wave speed as a generic thing. I think they're kind of using this as a generic form of the speed of light, which is c what we reserve for the speed of light. But this equation works for any wave, so many places you'll see this just written as v by normal, sane human beings. But the IB does what the IB wants, so you get c in the data booklet for the speed of any old wave. Doesn't have to be light. Okay, the wave speed only depends on the medium. And depending on the medium, those properties are different. Like, for a sound wave, say pressure, temperature, all those kind of things of the air might affect the speed of the wave. All right, but all we need to do, a wave then will travel at a constant speed moving through a medium. So a sound wave is going to travel the same speed through the air, right? Assuming like we're not changing the temperature of the air as it moves through or something. So the wave speed will be constant. And so we're just going to do distance over time, right? Our average speed equation. We can get away with this very sloppy version of speed, distance over time, because there's no acceleration, nothing like that. All right, and luckily I have a definition for both of these things. The distance traveled in one cycle would be a wavelength. That's how far the wave moves in one cycle. And the time it takes for one cycle is a period. So here's our equation for the speed of a wave. I take the wavelength and I divide it by the period. And just for fun, the period, we know, is 1 over the frequency. Right? Those two things are reciprocals of one another. And so if I want to get rid of these fractions, I can combine, plug in wavelength divided by 1 divided by frequency. Would you look at that? The wave speed is equal to wavelength times frequency. Amazing, very useful equation. You will use it a lot in finding any one of these things when you know the others. All right, so frequency of the wave, wavelength of the wave, multiply together to give you the speed of the wave. Very simple, beautiful, wonderful equation, the wave equation. All right. This also can show us, if we think about it, if I want to say solve for one or the other, wavelength or frequency, you could do either. They are inversely proportional. So for a given wave, which has a set fixed speed, again, let's focus on light, especially because we got c here, which is traditionally speed of light. Waves that have a long wavelength will have a low frequency and vice versa. And here's a little image to kind of simulate that. All right, so look at this. Let's say this is red light, or just our red wave here has a relatively long wavelength, and our blue wave has a relatively short wavelength. Well, notice if you watch here, focus on like this part of the screen. Every time the peak goes by, you can think of that as kind of a measure of the frequency. All right, so kind of a low frequency here. You can count or click or whatever every time the wave passes by. Down here, they're much closer together, and since they're traveling at the same speed, right, watch them move, same speed, the blue wave has a much higher frequency than the red wave does. It's much quicker moving to the right side. So because they're tighter together, the frequency is higher. And we'll get into this, but this generally corresponds to more energy. in the wave when it's got a higher frequency, shorter wavelength. Okay. There's two types of graphs you're going to see, and this can be tricky. Whenever you see a graph of a wave, you have to pause and think about what you're looking at, especially because your math brain might try to take over and you might assume you know what you're looking at. There's two graphs. The first is a displacement distance graph. There's no time on this graph. This is a snapshot. This is a picture. You'll have displacement on your y-axis and distance on the x. So y is the displacement of each particle from equilibrium like normal, and x is distance along the wave. This graph then will give you wavelength because you could measure the distance on x from peak to peak. But there is no information at all on this graph about period. So if you look at this graph and try and get the period, you're out of luck. You can't do it. On the other hand, you could have a displacement time graph, which is maybe a more traditional graph. But this shows a single particle on the wave moving as it moves with time. So it shows you one molecule of water as it moves up and down and plots its displacement versus time. Right? You can't do all of these things at once, so we're left with two different graphs, displacement distance or displacement time. So on displacement time, the distance, quote, from peak to peak on your x-axis would be the period, because that'd be the amount of time from maximum displacement back to maximum displacement for one particle of the wave. So really think about what you're looking at with the graph. If you make an assumption about what graph you're looking at, it's very easy to mess these up. All right, here's a displacement distance graph to show you what they look like. And the other trick is they look identical. They're both going to be sine waves or cosine waves or whatever. So you really have to read carefully with every graph, honestly, ever that you see, especially in IB physics. Read every axis like twice and really think about what is being graphed. All right, but so I got displacement here, distance here. So here's like a picture of the wave. So this is maybe a wave in the water with a couple little markers on it. And so I can see the red and the green marker are more or less at their equilibrium positions, and the blue is kind of dipped down at this instant in time. This is like we took a photo, right? This is a snapshot in time. There's no time progressing in the picture or on the graph. But this is a snapshot. And I can see that the red marker is here, and the green marker is here, and the blue marker is here. So along the distance, physical distance of the wave, I can see where some different particles are. That's what this graph is showing me. Right, so of course I can get the wavelength here from crest to crest. All right, and one last thing to wrap it up is the other type of wave. We talked about transverse, which is what this would be. These things are moving up and down. There's a longitudinal wave, and it's just sort of the opposite. In this case, instead of being perpendicular to the direction of energy propagation, the particles move parallel to the direction of travel of the wave. So they move in the same direction. They move side to side while the wave goes side to side. Ooh, here's a fun one. All right. Sound waves is the most common one that you'll see for longitudinal waves. And so this could be a speaker or your vocal cords or whatever making a sound wave. And so they vibrate side to side. So whatever frequency of vibration is here will be the frequency of the wave that is created by that oscillation. This one especially almost is like an optical illusion, because if you watch this, it sure looks like, if you don't look too close, there's stuff moving from side to side. But watch any one given particle. They highlight a few in red so you can really focus on them. You'll see that every single particle of the wave is just moving from side to side. Right, like back and forth. There's nothing moving from the left side of the tube all the way to the right side of the tube. They all stay around their own equilibrium positions and just oscillate back and forth, whereas the wave itself carries energy from side to side. That's the idea. That's what a longitudinal wave looks like. Those are the particles of the medium. Again, usually we're looking at air molecules here bouncing back and forth, bumping into one another. All right, and so we just have different names for these. Instead of crests and troughs, we call them compressions and rarefactions. So there you go. So compressions are where the particles are very close together at a given point in time, and the rarefaction is where they're very spread out. Here's another one with a wave on a slinky, which you can do if you take a slinky and push it back and forth. You'll see it happen. All right, so there you go. Those are some of the basics of waves here to get you started. There is lots more to explore with waves, so we'll get into all of it. But those are some of the really important definitions and skills for reading graphs using the wave equation that you will need going forward. So have fun.